Continuing on in the 2023 AP exam, this is question 2. So if I kind of scroll down to the question, how many grams of Cl gas can be formed from 1.25 moles of aluminum chloride? So this first question is a mole ratio question in which kind of how I like to do this is kind of mark up the equation. So I need to find the mass of the chlorine, and I'm given the moles of the aluminum chloride over here. So I can tell it's a mole ratio problem because to find the mass of this, I know that mass equals moles times molar mass. So the molar mass, I can look that up on my periodic table. I don't know the moles though, so not directly at least. So I need to use a mole ratio to figure out how many moles of chlorine I have. So to do this, I'm going to take the moles of what I'm given, which is the aluminum chloride, and I'm going to multiply. I like to do it this way. I multiply it by a ratio where I put the unit I don't want on the bottom. So I don't want moles of aluminum chloride, and I do want the moles of chlorine, so I put that on the numerator. So by doing your ratio this way, moles of aluminum chloride cancels out, and that will give me my answer in moles of chlorine. And to fill in the numbers of your ratio, use your balance equation, because what I see is that for every 3 moles of chlorine produced, 1 mole of aluminum chloride is consumed, which means 3.75 moles of chlorine is produced. So now I can actually use this in my mass calculation. So we're going to convert this to grams. That's what the question's asking me to do. So this will equal 3.75 moles times the molar mass, use your periodic table, of chlorine, 35.45 grams per mole. The units will cancel, moles will cancel, and we're going to round our final answer to 3 significant digits because that's what I'm given in the question up here, 133 grams. That's my final answer for part A. Part B is a Hess's law question, and I like doing these ones. It's like a little puzzle. So I'm asked to calculate delta H in kilojoules per mole for reaction 1. Now I kind of wrote all over the top, so what I'll do is I'll write the equation again on top of this data table. We need to find delta H of this. AlCl3 gas produces Al gas and 3Cl gas using the data given. So it's a Hess's law problem. We need to change these. I'm going to call the first equation my target equation, and I'm going to manipulate these side reactions so that they will give me the target equation. And if I can do that, I'm going to add up all of these equations up, and then I'll add up all of these delta H's, and that's how we find the answer to our target equation. So let's look at reaction number 2. Look carefully at the states as well, okay, because that's important. Notice that the AlCl3 here is a product, but I need it to be a reactant. So I'm going to flip equation 2 so that the aluminum chloride is on the correct side. Now when you do that, you also need to flip the sign of delta H by multiplying it by -1. All right, so let me rewrite this so that we have a clear work here. So when I flip the equation 2, I'll get AlCl3 produces Al solid and 3/2 chlorine gas. The delta H here is going to be -583 kilojoules times -1 because I did flip the equation, so it goes from exothermic to endothermic. Equation 3, I actually don't need to do anything because notice the aluminum gas is a product here, and it's a product in my target above, so I can keep the equation exactly as it is, and that will actually help me cancel out the aluminum solid as well, which we don't want that in our final equation because that's not in our target. So you'll see by writing it down like this, I'll be able to cancel out the aluminum solid. So the delta H for this one stays the same because we didn't do anything. And then the final equation, so what I'm noticing here is that the chlorine gas, the monoatomic chlorine gas, is on the correct side. It's a product, but the mole ratio is wrong. So I have 2 chlorine gas molecules here. I actually need 3 of them. So to get 3, you have to, so just do a little bit of mental math. I need to multiply this by 1.5 or 3 over 2, which means I have to do the same thing to the delta H over here. So let's rewrite equation 4. This will become 3 halves chlorine gas produces 3 over 2 chlorine monoatomic gas. And the delta H, again, we have to do the same thing because I multiplied the equation by 3 over 2. I also need to multiply delta H by 3 over 2. Okay, now we're going to add all of this up as per Hess's law. And when I add this up, what I see is, let's cancel out the aluminum because it's a product over here and then a reactant. So it's produced and consumed. We can get rid of it. And that's good because it's not in my overall target equation either. This chlorine diatomic gas, there's 1.5 on the right, so as a product, 1.5 on the left as a reactant. It's produced and consumed, so it's also going to be gone from our overall equation. So here's my overall answer. When I add up everything, I get the same thing in my target equation. That's what we want. And then now we can add up all the delta H's. So use your calculator to do so. And you should get a total delta H here of a positive 1,274 kilojoules per mole. That's how we solve our Hess's law problem. All right, and then let's move on to maybe one more before I pause and do the next part. This potential energy graph showing energy versus internuclear distance for chlorine. Based on the graph, what is the bond length in picometers for chlorine? If you've never seen this kind of graph before, what this is basically showing you is the energy between two atoms. So in this case, I'm looking at the energy between two chlorine atoms. So when you see high energy, for example, up here, this 500 kilojoules per mole, what that means is the atoms are so close together. That's actually not that's not the proper bond, okay? So that would be so close together that their positive nuclei would be so close that they would be repelling. So this repulsion is going to end up giving this like high energy level. So that's not really the bond length there, okay? That's actually too close. And then when you see this part here where the energy is 0, what that means is these atoms are too far apart. So the energy is 0 here, as you can see on the graph. There is no bond energy per se because those atoms are too far apart from each other. So the best scenario for this bond between Cl and Cl, this perfect distance between these two chlorine nuclei, is represented here where the energy is the lowest, this negative energy. That's like your perfect zone. So anytime you have a question or a graph like this, you just remember that over here, the highest energy means the atoms are too close. The lowest energy is 0. Excuse me, not the lowest energy, but when the energy is 0, the atoms are too far. And then the lowest energy over here represents where it's like the perfect distance. And that internuclear distance is, in this case, 200 pm between these chlorine atoms. Okay, so it's always going to be this lowest peak or this lowest curve part on this graph that represents your bond length. Okay, now we're going to try to draw for question, we'll do one more here. We're going to try to draw AlCl bond length. It's 220 picometers and it has an average bond energy 425 kilojoules per mole. So they want us to draw this on the graph. So I know that for the aluminum and chlorine, the bond length, it's 220. So actually you can see these dots on this graph. I was just counting the scale. So I know that these intervals are 20, right? So like 20, 40, 60, 80, 100. So 220, let me clean this up a little bit. 220 is right here. So I know that the bottom of this curve is going to be here on this axis, but I also need to use this definition or this information here. 425 kilojoules per mole, that's the average bond energy. So that is going to be negative 400 is here, so this line is 450, so 425 is in between. So I know that the bottom of the curve needs to hit right there, approximately there. Okay, so my aluminum is going to look something like this, aluminum and chlorine. This is going to go further down, and then it'll approach 0 again. And you can check your answer on the AP answer key to see it in perfect detail, but it's approximately there to represent this 425 kilojoules per mole and this 220 picometer bond length. Okay, yeah, let's pause it there and then we'll come back to this VSEPR question in the next part of the video.